This next question is very similar to the previous one. Let me read for you. The diagram shows an experiment to produce a stationary wave in an air column. A tuning fork placed above the column vibrates and produces a sound wave. The length of the air column can be varied by altering the volume of the water in the tube. The tube is filled and then water is allowed to run out of it. The first two stationary waves occurs when the air column lengths are 0.14 meter and 0.42 meter. What is the wavelength of the sound wave? Now here I'm comparing both diagrams side by side from the previous problem and the new one. So the loudspeaker here is the sound source. And the tuning fork here is the sound source. This problem here talk about two loud sounds that was identified. And this one say that two loud sound, the first two stationary waves, so two loud sounds occur when the air column is 0.14 and 0.42. So in this case here, didn't give a numerical value, just a letter, and here a numerical value. So the approach is the same. So this air column is represented by two types of medium. One is air, the other one is water. The stand wave is going to be formed in the air section. To provide a better visual of this story, I draw on this side supposedly a second water level. So for this first water level, I have the sound is going to hit here the water, and this is the antinode, and it's going to reflect back just like this, forming that kind of U shape. So this is my first antinode, and the length here is, the problem has provided, is 0.14 meter. Now the water level is lower and is right here, node, and this is an antinode. Okay, so this draw is not very realistic because this section represents a quarter of a wavelength, so it's kind of half-half, but hang there. This wave is going to bounce back from this water level. This water level is working as a sealed, like if this tube or pipe was kind of sealed right here, but in this case it's sealed with water. So this is the length of the air when the second loudest sound is heard. Of course, it's not on scale. So to calculate the length of the wavelength of this tuning fork, I'm going to draw this red line that represents the half of a wavelength produced by this tuning fork. And we're having the same approach that we did on the previous problem. Half of a wavelength is equal to the whole length here, which is 0.42 minus the first loudest sound that occurs right here on the quarter of a wavelength. So this is 0.14. Pure algebra. So this is 0.28. So the wavelength is 2 times 0.28. Let me write this down for you. And the wavelength is 0.56 meter. So that's the length of a complete wavelength produced by this particular tuning fork, which is the option D.